All right, another part of what we're learning this week is about the atmosphere, kind of its composition and structure. So, moving with that theme along here, uh, oh yeah, one other thing this chapter does talk about what they believe is the origin of the atmosphere. And I've always believed God gave us a lot of curiosity. And that curiosity is to look at things, to examine them. I mean, I believe God created the earth, but I also believe that there is some curiosity that I can use to maybe understand how things evolved or changed or how He even did a little bit of it. So that's why we're going to talk just a little touch about the origins in this chapter. And then we'll go into composition and structure as more of it. So, so with that, we're going to talk a little bit about how weather can be impacted all over the globe. Say you have a lot of thunderstorms in the Saharas, and this happens sometimes. What happens is it pushes a lot of dust up, makes a dust storm. When it does that, that dust is transported across the Atlantic into the Caribbean, sometimes into the southeastern U.S. And you can see on the satellite all this dust coming across down here. So, and that dust originated in Africa. It has some airborne things that aren't too nice. And it also gets rid of tropical cyclones. Kind of a cool thing there. But it increases the algae blooms in the Gulf of Mexico or harms coral reefs. So even though this is a natural phenomena, it can have damaging impacts on our Earth. So weather can go from tranquil to very severe very quickly. Every aspect, almost many aspects of daily life are impacted by the weather. And the Earth is a system. That means it's made up of the atmosphere, the hydrosphere, water, geosphere, which is like uh, volcanoes or the things, geography, topography. Biosphere is plant life. Each one of those impact the other. So the hydrosphere, water, impacts the atmosphere. Oh yeah, the atmosphere then impacts the hydrosphere by bringing precipitation back. So each one of these systems is impacting the other. And the atmosphere is a thin part of this. Think about it. Half the mass of the atmosphere is within 18,000 feet or below the level of Mount Everest. So if you go up to the top of Mount Everest, you're over half the atmosphere is below you. So the lower layer of the atmosphere is considered the homosphere because that is where the gases are all mixed up. When you get above that, they kind of separate based on their weights. So we're not going to be dealing above that. So think about it. In our part of the atmosphere, you're breathing 78% nitrogen, 20% oxygen, not quite 1% of argon, a little bit of CO2, and some water vapor is going to be mixed in there as well. And maybe some other gases in the low end. So oxygen is a big part of our atmosphere. We need that to live. That 20%, guess what? It's 20% wherever elevation you're at when you're in the troposphere or even in the stratosphere. So what's that mean? Well, the atmosphere gets thinner the higher up you go. So that's why it's hard to breathe, even though the air is still 20% or 21% oxygen. There's just not as much of it there. Another thing, we just looked at aerosols, dust particles, volcanic eruptions can put things in there. Oh yeah, we humans do it too. Sometimes we have burning trash in our backyards, whatever. That sends dust particles into the atmosphere. Water vapor is another component. It's less than 4% of the lowest 1 kilometer of the atmosphere. It's down pretty low. But, 4%, it's fairly significant. It happens to give clouds and precipitations, which we kind of think are pretty important. And CO2, of course, provides life. Without it, you would not have plant life, which makes the oxygen we breathe. So Everything works together. It's amazing how that works. Pollution, a lot of it is man-made, but then there are other parts that aren't. You can see here an old small picture in Los Angeles. When I grew up in the 60s, I can remember going to Pittsburgh and hardly being able to breathe because the air was so bad. It is much, much better now. We have done a great job as mankind improving the pollution in the earth. So if you're wanting to observe and ask the scientific methods, one of the questions, for example, that I happened to be working on at the time was, why do thunderstorms diminish sometimes when they come across the Appalachian Mountains and move to the east side where I live? So I asked the question, and I asked it with a group of researchers from North Carolina State. We developed the hypothesis that it had something to do with the atmosphere's stability, which is the ability to have the air rise. We developed check that hypothesis out to see if that would work or not. We found that, well, it didn't really work all the way. So we looked at some other things, maybe amount of moisture in the atmosphere. And we checked that hypothesis, and it still didn't quite work. But then we started combining them, and we found a tool where we could actually predict that thunderstorms would increase when they got on the east side of the mountains and decrease, while other times they would decrease. And we're able to use that tool now to get an idea and help our forecast be better. And that's just how the scientific method works. You can see we've used atmospheric models such as the tornado chamber at Purdue University. There are mathematical models. Everything we're going to talk about in this course can be described mathematically. It can't be solved. None of the equations that I'm going to give you, or I'm not even going to give you any equations, really hardly. But if you were to look at the math equations that went with their atmosphere, they're in such a form that no mathematician, at least currently, can solve them. And with that means we have errors in our data, errors in our models. Oh yeah, we don't observe the atmosphere perfectly either. How do we observe the atmosphere? We have ASOS as one tool. It's a surface observing system. One of the cute things or fascinating things to me is here's a pole that goes up. Top of that pole is an anemometer or wind. The winds on Earth that we observe as meteorologists are 10 meters in height or 33 feet up. So we're not looking at the wind down here at your face. We're looking at the wind well above your level. So all these instruments here, the dew point, measure of moisture, visibility, clouds, temperature, precipitation amount, all of those are measured at the airport, mostly with an ASOS system. Why are they at the airport? Well, think about it. Planes land there. Planes take off there. If they don't know what the weather is, they can't do that, not safely. So that's why ASOSs are located at these fields. There's a cooperative network that brings a lot of information into the system where stations, and these are all volunteers that have allowed the Weather Service to put systems in their backyard to measure temperature, measure precipitation. And they're used for long term. Once a month, this information flows into the National Weather Service office. Then it's calibrated over the whole country. And it goes down to Asheville, North Carolina, and the National Climatic Data Center to be incorporated into a climate record. There's COCORAs, which are just local cooperatives of people looking at rain, hail, snow networks. If you're ever interested, they'll be glad to have you. Radiosondes do an upper air sounding. You see a whole bunch of people observing it. When I would go out and did a couple over the years, there's basically just one person there taking the balloon out and letting it sail. And you'll notice that balloon is not real big here. Well, not even quite as big as a person. But by the time it expands, it's going to cover a large area as the atmosphere gets thinner and wind up exploding. And these are just the instruments on that. Dropsondes go the opposite direction. They're put out of an aircraft. They have a lot of the same instruments that a radiosonde does, except they're going to drop down into the ocean. That's why they're only released over the water so that we don't hit somebody's head over land. They're mainly used in Hurricane Hunter aircraft, but they can be used in other systems out off the coast. Another tool we use is with radar. It's a great source. Satellite is another one. And this is just a temperature profile. One of the things I want you to notice is temperature always drops on average in the troposphere. So if you're at a mountaintop, the temperature is going to be falling as you go up. Now when you hit the stratosphere, it begins to warm again. And then the mesosphere begins to drop again. Thermosphere begins to warm. So you can see there's really wild fluctuations in temperature in the atmosphere. And we use those fluctuations to determine what level in the atmosphere, whether we're in the troposphere, stratosphere, mesosphere, thermosphere. Auroras are in the ionosphere, and they're basically caused by the solar wind. The more solar activity, the better chance that aurora is going to span over a larger and larger area of the globe, and you might actually see it. I can remember as a child seeing one time in Pennsylvania. I have never seen another one since. But I do know they get down into even as far south as Ohio sometimes, depending on solar activity. So, with all that being said, let's just take a quick peek. One more time. Here is a surface weather map. You're going to be seeing lots of surface weather maps. So, I just wanted to take a look at a station symbol right here. This station symbol has a temperature to the upper left, 25. Dew point to the lower left, a measure of moisture, 18. It has a wind barb. Notice the wind barb goes out to the west of that station symbol when it's to the west, and then there's a little barb on it, very small barb, only 5 knots. Small barbs are 5, big barbs are 10. But the end that's on is the direction the wind's coming from. So this is a west wind, and that is how meteorologists look at it, the wind that's coming out of the west. Here, for example, is a north wind and 25 knots of wind. Oh yeah, the air pressure is over to the right here on this symbol. And you'll notice it says 293. Well, if it's below 500, add 10 to it, and it becomes 1029.3. If it's above 500, I put a 9 in front of it, and you can get the pressures down into 998, 980s, in that range. So this is how you look at a weather map and how you look at surface data. So just looking at satellite, for example, today, up here is Ohio, and you can see there's some snow cover up in this way, especially across where it's clear here in Indiana and Illinois. But there is a batch of clouds coming up here. And I'm down here in southeastern Virginia, and I have clouds. And where are these clouds coming from? They're coming from the Gulf of Mexico and southwest southern Pacific is where they're rising up and over from. So kind of an interesting thing these clouds do. They tend to cover large areas. And where they come from is kind of important. If these clouds were coming out of Canada, there's not a lot of moisture available, is there? And you can see actually a cloud coming off of Lake Michigan right here, which is helping to bring a little bit of snow if you're in that part of the world. So other thing I wanted to just look at was a vertical profile of the atmosphere. We talked about that in the course. This is Jackson, Mississippi. All they have done here is put pressure on the left, temperatures on the bottom, and we plot dew point and temperature. Dew points are always going to be to the left or along the temperature curve. Why is that? Because they can't be above temperature. You're not going to get super saturated air. So here is a little bit of an inversion. It's actually colder at the surface than it was about, probably 1,000 feet up. So if you went back and looked at the surface weather map, you would see the cold front is actually south of Jackson, Mississippi, but not very far. So what has happened is 3 dimensions. This is the level of that cold air. We're back in the warm sector here. Even though the air is getting colder, there was a cold snap here. Other thing to look at, up here around 200 millibars, even above it up to 100, really starts warming up And I wanted to show you that at Minneapolis because it's an even better one. Right here is the stratosphere where it really warms up. So all this for another week here. If you have any questions, please don't hesitate to ask.